Okay, this is section 10.2 and 10.3. We're on problem 30, where it says that each team in an 8-team basketball league is scheduled to play each other team 3 times. How many games will be played altogether? Okay, so you got 8 teams in the league. Team A is going to play Team B. Well, that's not any different from Team B playing Team A, right? So the order of who's playing who is not going to matter, since A playing B is the same as B playing A. So 8 choose 2 would be how many times each team will play each other team 1 time. Okay, we need each team to play each other team 3 times. So I just simply multiply by 3. 3 times 8 choose 2. 8 choose 2 is 28. 3 times 28 gives you 84 games total that are going to be played. Okay? Problem 31 says that 4 couples attend a play and are seated in a row with 8 seats. How many arrangements are possible if the couples are seated together? Okay, so no matter what happens, the couples all have to be seated together. Okay, 8 seats. Okay, so are open currently. Have one of them be filled. Okay, and any of the 8 people can sit down. Okay, now that person's date has to sit next to him or her. That this person right here only has 1 date. Okay, so whoever has sat in the first seat, that other person has to sit right next to him or her. Okay, so now 2 people have sat down. There's now 6 people left without a seat. Okay, there's 6 open seats available. So have any one of the 6 sit down. This person's date has to sit next to him or her. Again, this person only has 1 date. Okay, so now 4 people would have sat down. So 4 people still have to be seated. So have any one of the 4 sit down again. And this person's date has to sit next to him or her. Now 2 people left. Okay, so have any one of the 2 sit down. Okay, this person's date, him or her, whoever's last seat, has to sit down there. So now all 8 people would be seated. Okay, so basically what this comes down to is taking 8 times 6 times 4 times 2, which is the 384 different arrangements are possible. Okay. Problem 32 says that a palindrome is a word that reads the same forward or backward, such as noon or madame. How many different 5-letter words, real or imaginary, are palindromes? Okay, the real or imaginary, what I mean by that is like maybe it's a real word that you use in everyday English, or maybe it's some imaginary word, okay, like XZXZX, okay, or something like that, or all Q's or something. Those aren't words, okay? So it could be real or imaginary. You just make sure it's length 5. Okay? 26 letters are in the alphabet, so we got 26 choices for the first letter. Okay? Now, in order to be a palindrome, it needs to read the same forward or backward. So whatever this first letter is, this last letter has to be exactly the same. There's only 1 choice. Okay, so if this was the letter M, this also has to be the letter M. Okay, if this was the letter D, this also has to be the letter D. Okay. Now, they didn't say anything about not repeating or anything like that. Okay, so all 26 letters are available for the second spot. Well, in order to be a palindrome, the 4th spot has to be exactly the same thing as the second spot. Okay? Now, I don't care what letter goes in the middle, since if you read this forward or backward, that middle letter is going to be the same, located in the 3rd spot. and not have to be matched with anything. Okay, so really that can be any letter we want. Okay, if you take 26 times 26 times 26, I'm getting 17,576 words. Now, maybe a more interesting question, and I don't know the answer to this, but I wonder how many of these words are actual words that you would use in everyday language. Okay, so probably another mathematical question, but anyway. Problem 33 says that a barcode for merchandise consists of 10 rectangles. There are 2 possible lengths and 4 possible widths for each rectangle. How many barcodes are possible? Okay, well, you got 2 possible lengths and 4 possible widths for each rectangle. Well, forget about the 10 rectangles. How many ways can we make a 1 rectangle? Okay, well, I have to choose a length and I have to choose width. There are 2 possible lengths and 4 possible widths. So there's 8 possibilities for making 1 rectangle. Okay, now I need 10 rectangles. So basically, I do the same thing 10 times. Okay, or take 8 to the 10th power. 8 to the 10th power gives you 1,073,741,824 barcodes are possible. Okay, so just in this arrangement, where there's 2 lengths and 4 widths, 10 rectangles, you can make over 1 billion barcodes. Okay, so somebody trying to break the code or something like that is going to have a real tough time doing that. Okay, if there's over 1 billion of them. Problem 34 says that a grocery store stocks 30 different kinds of cereal, of which 10 are unsweetened. Okay, so 20 of them would be sweetened. In how many ways can you choose 5 different kinds of cereal if you want exactly 2 of your choices to be sweetened? Okay, so there's 20 sweetened and 10 unsweetened to give 30 total. Well, let's see here. I need to choose the number of sweetened and then have the other 3 be unsweetened. Okay, and I'm choosing 5 total, and exactly 2 of them need to be sweetened. Okay. So 20 choose 2. There's 20 that are sweetened. You're going to choose 2 of them since we want 2 sweetened cereals. Now, the other 3 have to be unsweetened. So I got 10 total in the aisle that are unsweetened. I need to choose 3 of them. That way I've got 5 total that are selected. Okay? By the way, why am I using combinations here? Well, it's because order doesn't matter, right? So we looked at a problem earlier with somebody buying 3 cereals and going to purchase the 3 cakes, Cheerios, and Apple Jacks. Well, it's not going to matter, right? The same transaction is going to be made regardless of whether you say Kicks, Cheerios, or Apple Jacks, or Apple Jacks, Cheerios, or Kicks. Okay, same deal here. I'm choosing 5 cereals. Now exactly 2 of them are going to be sweetened. Okay, so whatever order I say of those 5 cereals with 2 sweetened is not going to change. Okay, so if I say 5 cereals like Cakes, Cheerios, Apple Jacks, I don't know, Raisin Bran and Fruit Loops. Okay, if I mix up those 5, it's not going to matter. Okay, so 20 choose 2 gives me 190. If you were to check that, 10 choose 3 gives me 120. So all I have to do here is take 190 times 120, and that gives me 22,800 ways that are possible. Okay. Let's maybe do problem 35 here. So problem 35 says that for a cross-country meet, Each school is allowed to enter 5 runners. Yorkville High has 17 runners on its team, of which 8 of them are seniors. In how many ways can the Yorkville coach pick his 5 entries if he must enter 2 seniors? So no matter what he does, two of the 5 people that are running have to be seniors. Okay? Now, if John and Ricky are the 2 seniors, it's not going to matter if we go John and Ricky or Ricky and John, right? So those 2 have been selected, and now there's 8 seniors. Okay, you're gonna select 2 of them. The other 3 people have to be freshmen, sophomores, or juniors. Okay, so there's 17 runners on the team. If 8 of them are seniors, the other 9 runners would be freshmen, sophomores, or juniors, okay? And we need 3 of them to be freshmen, sophomores, or juniors. Okay, that way we've got 5 total being selected. Okay. 8 choose 2 should be 28, and 9 choose 3 should be 84. Okay, so if I take 28 times 84, I get 2,352 different ways. Okay. So some of the problems here are getting to be such that you've got multiple combinations involved. Okay, and that's typical to have those being later on. Again, this is what I was talking about this chapter. Like nobody is telling me that I had to use the fundamental counting principle, or I had to use combinations, or no, I have to figure that out on my own, right? And so once I've done that, then I'm using that counting technique to solve. Okay. Why don't we pick up with 36 in the next video? In the next video, that'll be the last one for this chapter.